So the last thing we really have to talk about is pressure. And what is pressure, and how we measure it, and how we convert it, et cetera, et cetera. Pressure is a physical quantity. It's the amount of force applied per unit area. Pressure, P, is equal to force divided by the area. There you have it right there. It's that simple. If we do a little unit analysis, what do I measure force with? What is my unit for force? And I'm recording this so Mr. Petrus can hear the lack of answers. Yep, it's a Newton. Area measured in, any ideas? It's a square something, right? Square centimeter. Let's do meter squared. Meter squared. A Newton per meter squared is a pressure. Now, like many other units in physics, we've often given the complex unit a different name to honor someone and to make it a little simpler. The person that we've named this unit after, his name is Pascal, so it's a P-A, capital P-A, a Pascal. All right? So what's 1 Pascal? 1 P-A is equal to 1 Newton, all right, spread over 1 meter squared. Now that's just the physical meaning of pressure. I haven't talked anything about gases yet. That's just pressure. It's how much force is being spread over a particular area. Let's now talk about how gas pressure is affected. So, don't worry about the thumbtack. That just kind of goes with my writing. No big deal. Let's talk about now the pressure of a gas. And I'm just going to bring the whole thing up, okay? And I am going to, in terms of this picture, this is just a bunch of particles moving around. If you're drawing the picture in your notes, just draw a rectangle, put your gas particles in it, and put some arrows showing the fact that they're moving kind of chaotically. And I do want 1 or 2 particular arrows showing the particles bouncing off of the walls of the container, because that's what pressure is all about. It's all about the particles striking the walls. As particles move around in a gas, they travel in a straight line until they either run into a wall or they run into another gas particle. If they run into a wall and they bounce off that wall, they will apply a force to the wall. They have a very tiny area, and that force will impart a pressure on the surface of the wall. Now that's for 1 particle. But in a gas, there are billions and billions and billions and billions of particles. So then how does a balloon then maintain its shape and its pressure? It's because the particles are bouncing off the balloon, and they're maintaining that shape. Imagine that you could take a grocery bag, plastic grocery bag, and in your house there is one of these dopey flies. You know the dopey flies I'm talking about? If you live in an old house, you know what dopey flies are. They come out in the spring and they bounce off the ceiling. You never see that before? They're stupid. Trying to go to sleep, they're bouncing off the ceiling, driving you crazy. All right, if you know what dopey flies are, you know what I'm talking about. So let's imagine you could catch one of those dopey flies and stick it into the bag and kind of hold the bag shut. What would you see? What would you see if you had a dopey fly in a bag? It would freak out, but what would you see on the outside? You'd see it go, because it would hit the side and then it would hit the side again. Every time the dopey fly hits the side of the bag, it exerts a little bit of pressure. Now let's imagine you could catch more dopey flies, 30 of them, put them in the bag. What's the bag now going to start to do? Move. It's going to push out, push out, push out, push out. Let's say that you then, if the flies were very small, and you could fill it with thousands of dopey flies, what would the bag look like? It wouldn't float. What would it look like? It would be pushed out. Why? there's flies striking the surface constantly, and the bag is not able to get back to its original kind of, empty shape. So because there's so many flies in there striking the surface of the bag would push out. When you blow into a balloon, you're filling it with a bunch of dopey flies. And these particles are constantly bouncing around in there, but at any point in time, there are gas particles striking pretty well every surface of this balloon. And therefore, it's pushed out because there are these dopey flies running into the wall of it. Again, if we could get into our magic school bus and zoom in to the surface of this balloon, we again would see some dopey fly action. You'd see the balloon would actually stick out and bulge every time a particle struck it. But because we're big and the particles are small, we can't see that. But that's what causes pressure in a gas. All these little particles striking the walls over and over again. The SI unit for pressure is the kilopascal. Actually, it is the pascal, but we use in this course the kilopascal, and that's because a pascal is so small. Okay, so some very important temperatures and pressures that we will be encountering in this course. So chemists have chosen temperatures and pressures that are very important to chemists and have kind of set them as special or standard temperatures and pressures. And we use these temperature and pressures in various situations and calculations. Standard temperature and pressure, STP. STP has been defined as being two important values that kind of get their values in different ways. 0 degrees Celsius, that's a fairly obvious number and why it was chosen. Ice, water, transition, 0 degrees Celsius. 101.3 kilopascals. You might think that that's an odd number to choose as a special pressure, but that pressure has been determined to be the average of the atmospheric pressure at sea level, so at a particular altitude, and that's defined at sea level, all over the world. So if we were to take that pressure of the atmosphere above us and measure that at different places in the world and take an average of all of those pressures, we end up with this number of 101.3 kilopascals. All right? Now let's talk a little bit about atmospheric pressure just for a moment before I talk about the other pressures and temperatures. Here, let's turn this on and let's start up the notebook. And let's see if it will start up. Oh, the speed of the computer system. Oh, so exciting. All right. So essentially, right, can I do a shape here? Let's draw an Earth. That's not an Earth. I can't draw shapes with this device. Nope. So we get to draw on it. Let's draw an Earth. Earth. Right there. Okay? And I'll draw myself on the Earth. There I am, on the Earth. And above the Earth, we obviously have atmosphere. I'll just put some air around the Earth. That's horrendous. But that's the air. That's the air around the Earth. And above us, there's always a column of air. Whether we talk about us or, over top of a surface like a football field, it doesn't make any difference. But above us, there's always a column of air. And that air gets thinner as you go higher up, right? This is thin air, and down here it's essentially thick air, all right? It's essentially thick. And gravity pulls down on that air, Fg. That's why the air sticks around on the surface of the Earth, because gravity is pulling it down. And that means if gravity is pulling down on the air, then that air has weight, all right? Gravity is weight, by the way. What's the weight of the air above us? Well, we can measure that weight by reading the pressure. And the pressure on average at the surface of the Earth, that pressure is about 101.3 kilopascals. All right? Now, 101.3 kilopascals. If we get rid of the kilo, that's essentially 101, and then I move the decimal place over 300 pascals, right? And if we think about what a pascal is, remember yesterday, 1 pascal is equal to 1 Newton over 1 meter squared. Which means if, let's say that this was a meter squared. Let's say right here, that area above my head is about a meter squared. If that's a meter squared right there, if I've got 1 meter squared right there, then that means instead of 101,300 pascals, there's actually 101,300 newtons of air over that meter over my head, right? If I measured a meter over my head, that much, that's not too bad, it's about a meter. Then right now, the air above me has a weight of 101,000 newtons. 101,000 newtons. Now a newton is not very much, but 100,000 newtons is a lot. Right here I have my 1 kilogram mass. That's 10 newtons. Right now, above me, even though there's a roof and then there's multiple floors above me, that air pressure comes in and fills the room. I could do this outside, it makes no difference. But right now, there is 101,000 newtons of force being pressed down on my skin, on my shoulders, due to the air above me. That's a big pressure. That's a lot of weight. Now, we don't sense this because humans have evolved in the gravitational field that is down on the surface of the Earth, and we've evolved with this air always around us. So we are just simply accustomed to this huge pressure of the air that's piled up on top of us. But we can sense when we go to an area where there's less pressure. If we get into a plane and we fly to a location that is higher in the air, so let me get my plane here. So here we go. So now I'm flying around up here. There's my plane. It's a horrendous plane. Flying around in my squiggle plane. And now there's only that much air above me. It means that there's less pressure because I don't have to hold up as much air. And right away, my ears tell me, whoa, less pressure, uncomfortable. This is horrendous. I don't like this. I need some gum. Got to chew on that gum. So the pressure equalizes until when you land. And then now there's less pressure in your ear, your middle ear, and it pushes in and it's very uncomfortable. But we have an incredible amount of air above us that is weighing us down, but we're used to it. Again, just another calculation to put it into some perspective. If we assume that G is equal to 10 newtons per kilogram, we all know as physicists it's 9.81. I know, but let's just make it 10 for ease of calculation. That means if we are being weighed down by 101,300 newtons, if I divide that by 10 newtons per kilogram, then I end up with taking one of these zeros away, 10130, 10,000 kilograms of air exist above us. That's what we're holding up. We literally hold up 10,000 kilograms of air every day. So if somebody says, get off the couch, quit playing video games, go do some exercising, you can say, are you kidding me? I'm holding up 10,000 kilograms of air right now as I speak. I'm doing workout all the time. Oh, 10,000 kilograms. No problem. So that's where this number comes from. This number, 101.3 kilopascals, is the average air pressure over the surface of the Earth. And that's an important thing. That's an important number because that's the way we exist. We exist in that air pressure. Same with the molecules, same with the water, same with the ice. So if we want to study the substances on the planet Earth, then we need to be worried about that pressure, all right? 0 degrees Celsius, That's where water melts, freezes. That's important as well. SATP, that stands for standard ambient temperature and pressure. Also a very important temperature and pressure. These have been decided by chemists as being important numbers pertaining to laboratory conditions. In a laboratory, the temperature is usually around 25 degrees. It's a little warmer than what we consider room temperature, 23. And that's because there are usually motors running, and maybe there's a refrigerator to house some materials, or there's pumps going, or you're running a Bunsen burner, or you're doing this or doing that, which tend to generate heat. So laboratories tend to be a little warmer than regular rooms, 25 degrees Celsius. The pressure in a laboratory also tends to be a little lower than atmospheric pressure, because most laboratories have venting fans that suck air out of the lab and then vent it to the atmosphere. So if you're working with chemicals that are producing gases that you don't want to be breathing in, right? You have fume hoods that are drawing that air out of the building and then out into the air. So usually the sucking of the air out of the laboratory brings the pressure down a little bit. So standard ambient temperature and pressure basically indicate laboratory conditions. When we look at our periodic table and we look at all of those states, liquids, solids, gases, those particular states are what you would see under standard ambient temperature and pressure. So we define our states on the periodic table, what we would see in laboratory conditions. Okay? So one is more atmospheric, right? Out in the open, what you would see. The other one is more laboratory conditions. On the periodic table, it's SATP. They're what we would see under laboratory conditions. Okay? Other units. Taking standard pressure and converting it into other pressure units, because we will be using other pressure units in this unit. Here we've got atmospheres. Atmospheres is a unit that astrochemists would use. An astrochemist would be someone who studies the chemistry of materials on other planets, and it essentially is the way we compare our atmospheric pressure to other planetary atmospheric pressure. So we say on Earth we're subjected to 1 atmosphere, but if you went to Jupiter, there would be, hundreds of atmospheres of pressure. 760 millimeters of mercury. That has to do with the way we used to measure pressure. We also call it torr, because Torricelli was the one who invented that. Okay? And then we also have pressure measurements like PSI, pounds per square inch. And we use PSI for like regular industrial things. And just to finish our little note on pressure, we're going to do some conversions here, because in the end, we want kilopascals. We're going to be doing some calculations where kilopascals is the important calculation. So we need to be able to convert these to kilopascals. Using the units on the previous page, remember, when I first introduced you to conversion factors, if I had an equality, I could easily turn that into a conversion factor. So if I am going to convert atmospheres to kilopascals, then I'm going to create a conversion factor that has me get rid of atmospheres and has me get the unit of kilopascals. I need kPa on the top, and I need atmospheres on the bottom. What numbers am I going to put in here in order to get that to be a true statement? So all we're doing is generating conversion factors. 1 atmosphere, by the way, is a whole number defined that way. So I'm looking at 3 significant digits here. 177, and that's kilopascals. Okay? I'm really only going to be wanting to turn it into kilopascals, because that's the number that's found in many of our equations. So it's always going to be 101.3 kilopascals on the top. What's going to go on the bottom of this one if I want to convert it? Carissa? Yep, 760 torr. Again, 3 significant digits throughout this. Yep. 86.6 kilopascals. We like it? And the last one, again, 101.3 kilopascals. What's going on the bottom of this one? 14.7? 14.7 PSI. PSI stands for pounds per square inch. Now I believe you have that list on your information sheet on your periodic table. Just check to see that it's there. So you really don't have to memorize them, but you do know how to use them. You do need to know how to use them. What do I have here for a number? Taylor seems to be filling in. What do you got? 141? 241 kilopascals. Okay? There is a little question in the book that deals with that.